Hello and welcome to this module. We're going to be looking at discrete Fourier transform and normal matrices in a few lectures. Let's begin. Okay. First, let me go back to this circulant matrices. We studied them briefly in one of the lectures a few weeks ago. I introduced what they are, and we looked at this Fourier basis and how this Fourier basis ends up being a set of eigenvectors for circulant matrices. It's sort of a very nice and interesting structural result. Let's revisit that and get started. Okay. So you may remember that there was this FIR filter with a certain impulse response, H0 to H7 for instance, and then if you have an input and an output, this circulant matrix models this convolution that happens here and gives you the output. So, the input is a vector, we can multiply by this circulant matrix, of course with some zeros to make sure that things work out, so that the convolution becomes modeled as circulant matrix multiplication. So, now this is a very important idea in all of digital signal processing. So, this matrix, circulant matrix, plays a very important role. So, notice how this matrix is defined. The first column is H0, H1, H2 till H7. Okay, so the first column goes like that. The second column is one circular rotation of the first column. You take the last guy, put it in the first, and then rotate everything. Rotate everything. If when you go to the third column, it's a circular rotation of the second column. Okay, hopefully you see that. So when you circularly rotate this guy, you get the third column. You circularly rotate this guy, you get the fourth column. So on, so on, so on, till you get to the last column. Okay. You can also equivalently see this as row rotation. You take the first row, the first row is H0, H7, H6, so on. It's sort of not the same as the first column, but sort of is inverted a little bit. But still, the second row, if you see, is a circular shift of the first row, right? So, the first row has been taken, is circularly shifted to the right, the last guy has come to the first, you got the second row like that, okay. So, circular shift of column, circular shift of row, both are the same. So, you get a circulant matrix, okay. So, it turns out the Fourier basis is an set of eigenvectors for this n cross n matrix, and let us revisit that and confirm what that is, okay. So, here is the Fourier basis. To define the Fourier basis, we need this nth root of unity. Okay, what is the nth root of unity? It is basically this symbol omega, which is e power I 2 pi by n. So, I will talk a little bit more about this in the ensuing slides. What is the nth root of unity, what it means, etc. For now, it is a complex number. It is defined as cos 2 pi by n plus I sin 2 pi by n. Okay, an interesting fact about this number is omega power n is 1. If you raise this to the power n, you get e power I 2 pi, and e power I 2 pi is 1, right. So, imagine e power I 2 pi by n on the unit circle, right. So, all the values are on the unit circle, 2 pi by n is an angle. We will see this picturization in the ensuing slides, but this is the Fourier basis is defined using this omega. Okay, the definition is quite simple, but let us just spend some time and make sure we understand the notation and everything. Okay, there are n Fourier basis vectors u0 to un minus 1. These are all eigenvectors of M. Okay, each of these guys is an eigenvector of M. So, this is a property we saw before, but anyway, so believe me, we'll test it later, we'll prove all this later, but for now these are all eigenvectors of a circulant matrix. So, what are these vectors? The first vector is very simple, u0, it is just 1 by root n all ones. Okay, and what is the kth vector? Any general vector u0 to un minus 1, the uk for a general k is 0, 1, 2, so on till n minus 1. For a particular value of k, what is the vector? It is 1 by root n, that is just a normalization. What you have here is a very simple series of powers of omega as the coordinates. First coordinate is 1, second coordinate is omega power k, third coordinate is omega power 2k, so on till final coordinate omega power n minus 1 into k. Okay. You can imagine the first coordinate as being omega power 0 into k, right. Omega power 0 into k is just 1, right. So, that is why I have written it as 1 here. So, you can say it goes from omega power 0k, omega power 1k, omega power 2k all the way till omega power n minus 1k. So, from 0 to n minus 1 there are n values here. So, those are the n values in this vector. Okay. So, this is uk. Okay. This is the kth vector. It is a complex vector, right. So, it is a complex number. Every coordinate is complex. It is in general, yeah. So, there is e power I. So, each of these guys are complex. So, it is like a complex looking thing. But for k equal to 0, notice what happens. If you put k equals 0, all of these guys become 1, right. It is very easy to see. If you put k equals 2, it is going to be 1 omega squared, omega power 4, omega power 6, so on, right, till omega power n minus 1 into 2, like that. Okay. 3 will be omega power 3, etc. all the way you can go up to n minus 1, k equals n minus 1. So, you will get the last one being 1 omega pi n minus 1 omega pi 2 into n minus 1, so on till omega pi n minus 1 into n minus 1. Okay. So, hopefully you see these n vectors. These are like sort of slightly more complex vectors than maybe you have seen so far. Maybe you are used to seeing in very small nice vectors with integer values. These suddenly have complex values, a little bit more confusing, but they are at some level they are simple in some sense, right. So, always remember Fourier basis in terms of these omegas. Okay. So, if you write it in any other form, it may be a bit confusing. In terms of omega, these are very simple vectors. Interestingly, these are eigenvectors of this matrix M. Now, let us use these ideas to say something about the Fourier basis. So, in fact, the Fourier basis is a very special basis. It has two very special properties, or one very important property. The property is that the Fourier basis is an orthonormal basis. Okay. So, you may be very surprised that this 1 omega square all over the place we have written something. How is this vector orthonormal, right? So, why should it be orthonormal? So, the powers of omega make it happen. Okay. So, let us prove it. To show that the Fourier basis is orthonormal, you have to show that this norm of uk is 1, right. So, each of the norms is 1. Okay. So, omega is e power I 2 pi by n. And this uk is complicated looking vector 1 by root n 1 omega per k omega per 2k omega per n minus 1 into k. How is this going to have norm n? Okay. For that, to understand norm, we need to write norm uk squared, and that will be 1 by n. Okay, right. I am squaring norm uk, right. So, if uk into uk conjugate, so uk conjugate will be 1 bar omega k bar omega 2k bar, etc. Then uk itself is 1 omega k omega per 2k, etc. And then this 1 by root n will come both in uk and uk bar, I mean uk Hermitian. So, that will become just 1 by n. 1 by root n into 1 by root n is 1 by n. Okay. So, this is the expression for norm uk squared. Okay. So, this has to be equal to 1 if I claim that my orthonormality is correct, but then I need to evaluate omega k bar. What is the conjugate of omega k? Okay. Omega k bar is cos 2 pi k by n minus I sin 2 pi k by n. Now, this minus sign can be moved inside. Cos, of course, nothing happens to it when minus angle goes in, but sin minus is minus. So, this you see is nothing but omega par minus k, which is actually omega par n minus k. Okay. I will retain it as omega par minus k because it is useful to have plus and minus. Okay. So, as long as you are not exceeding too much, so plus and minus is very nice. So, we will keep it like that. Okay. So, omega k bar is the same as omega par minus k. So, now if you substitute that back here, okay. So, anyway, let's see that in the picture. So, the conjugate of omega par k is actually omega par minus k, which is the same as omega par n minus k. So, the angle is minus 2 pi k by n. Okay. So, that is the relationship. Now, if you plug that in back in here, omega par k conjugate is minus k, 2k is minus 2k minus n minus 1k. Notice that these guys will cancel and you will just get 1 plus 1 plus 1 plus 1 plus 1, and then n and n will cancel and you get 1 magically. Okay. So, this Fourier basis, this complex looking Fourier basis that we are writing down here with a lot of complex numbers has norm 1. Okay. That is the first step in the Fourier basis. And like I claimed, the Fourier basis is an orthonormal basis. Okay. So, not just any old basis, it is an orthonormal basis. Okay. So, to show orthonormality, I have to show that uk and say uk plus 1 or any other any two different uk and ul for instance, they have to be orthogonal with each other. Okay. So, that is what we are going to show next. Okay. So, we are going to show orthogonality of Fourier basis vectors. Okay. So, here is a very interesting sum property. It is a very non-trivial property. We will prove it. We will prove it a little bit later. But here is a property. You might want to remember this very cleanly. So, supposing you start with the nth root of unity and k is any integer. Okay. If you do this kind of a sum, right, 1 plus omega par k plus omega par 2k plus so on till omega par n minus 1 into k, right, you have to go up to n minus 1, that is important. You go up to n minus 1 and then any integer k is okay. If k is a multiple of n, this ends up being n. Okay. So, that is very easy to see, right. If k is a multiple of n, all these guys are 1, So, 1 plus 1 plus 1 is n. If k is not a multiple of n, this ends up being 0. Okay. So, this is a very surprising little property. It's got a lot of powerful applications. In particular, it shows It's useful in orthogonality of Fourier basis vectors to show that property. Okay, so this little sum here is sort of like even though there are a lot of complex numbers in the definition, we saw that this omega was so many complex numbers, but if you raise it to the power k and then you add up from 1 to n minus 1, the sum is almost like it can be only n or 0. Okay, 0 or 1, it goes to binary, it goes from some continuous complex world to a discrete world. Okay, only two possibilities, n and 0. Okay, so it's a very interesting relationship. A lot of people consider this a very beautiful relationship for mathematics. That's something you go from very complex world, you go to a very simple answer at the end of it. Okay, so this is a property. We're going to use it to show orthogonality of Fourier basis vectors. We'll come back and prove this later. Okay, so what we need to compute is the inner product of uk and ul, and k and l are two different numbers in the set 0 to n minus 1. So this defines two different Fourier basis vectors. Uk of course is 1 by root n 1 omega per k, ul will be 1 by root n 1 omega per l, omega per 2l, so on, and the k and l are different. These two vectors I have to show are orthogonal. So I need to evaluate this inner product uk ul, and that is the same as 1 by n. The n comes because of obvious reasons. 1 into 1 bar plus uk into ul bar plus omega per k into omega per l bar, omega per 2k into omega per 2l bar, so on. Okay. So now what do we know about conjugates? We know conjugates. We can just subtract the powers. I mean negate the powers. Omega per l conjugate is omega per minus l, and so on. Okay. So now we can add up these things, right? Omega per k into omega per minus l is omega per k minus l, 2 into k minus l, n minus 1 into k minus l, etc. Now what is this? Using the sum property, what is this if k is not equal to l? If k is not equal to l, this is 0. Okay, and of course if k is equal to l, this becomes n, and n by n it will become 1. Okay, so that was the orthonormality property. So just by this wonderful little proof, we are able to show that the Fourier basis is orthonormal. So the Fourier basis being orthonormal is a vital piece of detail. So I think that is something that you should remember. The Fourier basis is an orthonormal basis. The dot product of any two different, the inner product of any two different Fourier basis vectors is 0. The norm is 1. Okay. So the only thing I have not proved is this little fact here. I'm not going to do it in this lecture. I will leave it as an open problem for you. If you know the answer, if you know the proof, you can look it up in Stack Exchange, etc. If you know the proof, please post it on the discourse forum, and you can have a discussion about the proof with the instructors and others. Okay. Thank you very much for your attention. So a couple of quick proofs here. First is circulant matrices are normal. Okay. So we saw that circulant matrices need not be symmetric, but they are normal. So how do you prove it? M is like this, M Hermitian is like this. Okay. So you just go through it, columns become row, and then you do the conjugations. And then you have to look at the product. Okay, so let's look at M Hermitian and M Hermitian M. Okay, let's look at the I comma ith term. I comma ith term is first row multiplied by the first column, right? First row multiplied by the first column, or second row multiplied by the second column, or third row multiplied by the third column. If you do any of these products, you will see that the I comma ith row is always ith entry of M Hermitian, M times M Hermitian is always of this form. H0 bar plus hi bar plus hn minus 1 hn. You can check this. You take the first one, multiply, you get the same expression, right? Second row multiplied by the second column, you get the same expression. So I comma ith term is the same. Curiously, the other one is also the same. I'll leave you to check this. You take, the ith row of first row of this guy, M Hermitian, multiply by the first column here, you get the exact same expression. Okay, you can check that this has to be true. Okay, I comma I is the same. You can also do I comma I plus 1. First row multiplied by the second column. First row here multiplied by the second column here. You will see that the expression is exactly the same. You get this h0, h1 bar, hi plus 1 bar, hn minus 1. Of course, there is no hn. Hn is the same as h0. So it becomes h0 bar. Both of these are exactly the same. So you can push this to I comma I plus j. Of course, I can do I plus j, I have to do modulo n, as in I have to take the remainder when I divide by n. So that I will denote as the square braces n. Okay. So if you do that, you will see that this expression and this expression are the same. I am not going to go into detail. You can check that this will also be exactly the same. So circulant matrices are normal, and no wonder they have a unitary, they have a orthonormal basis of eigenvectors, and curiously enough, for circular matrices, the Fourier basis ends up being that basis.